Okay, so good afternoon, everyone. So we start with number 6 in the tutorial, week 4. So number 6 is about solving ax squared equal b in 2 ways. So which one is more costly? Okay, so we will do it on a piece of paper. So you can see that. So if you have question, then please put your question in the chat box, okay? So you can see that we have a square x equal b. So this one tutorial week 4. So question 6. So we solve a square x equal b in two ways. Yeah. So the first is you compute a square. Then you solve a square x equal b. Okay. So somebody have music, so please can you mute? Thank you. So a square, so remember a square is, you write down the matrix A like this. So A11 up to A1n and AN1 up to ANN, right? So you write down again, so A11, A1n, AN1 up to ANN. So how do you compute the first entry? So suppose, so this one is a matrix B, yeah? So what is B11? So B11, you just take this row, right? And then you multiply with these columns, entries by entries, and you sum it up. So will be A11 plus A12, A21, and so on up to A1n, AN1. So how many flops? How many flops you need to compute B11? So how many flops? Well, how many multiplication? So n multiplication, right? So n multiplication and n minus 1 addition, right? So this one is 2n minus 1 flops, right? Well, if n is very big, then you can say that's about 2n. 2n for n large, yeah. So then how many entries do you have? How many entries do you have for the matrix B? How many n square, yeah? So then you have n square entries multiplied by 2n. Okay, so then computing B text, it's about 2n cube flops, yeah? Flops for floating operation. Okay, then after that you solve bx equal b. So now, so this one is only step 1, yeah? So only step 1. Okay, but then step 2 you have to solve bx equal b. So solve bx equal b. So assume that you use Cholesky factorization. So Cholesky factorization, then it takes you to n cube over 3 flops, yeah? And then you have back and forward substitution. So 2n square flops. Okay, so then totally you have, so in total, the first approach will take you to n cubed plus 2n cubed over 3 plus 2n square flops, yeah. So which is about an square over 3 plus 2n square for the first methods. Okay. So now how about the second method? Now for the second method. For the second method, you solve AY equal B, right? So then suppose you give Cholesky factorization. So Cholesky factorization of A, right? And it take 2n cubed over 3. Yeah. And you use back substitution, yeah. So back substitution, so back and forward substitution. You got 2n square. Okay. And now after that, you solve AX equal Y. So now do you need Cholesky again? Do you need to compute Cholesky factorization again? Do we need it again or not? Yes or no? No, right? Because you computed already here. So that's why you need only back substitution and forward substitution. And this one takes you to n square. Okay, so then total in this case, you have 2n cubed over 3 plus 4n squared. Okay. So remember in the first method, you have, so remember in the first method, you have 2n squared plus 2n squared over, sorry, 2n cubed plus 2n cubed over 3 plus 2n squared, yeah? And here you have 2n cubed over 3 plus 4n squared. So which one is more flops? So the first or the second? I mean, here we have to assume large n. Yeah. So which one? The first or the second? The first or the second? So remember the first is, so the first, yeah, so the first compare with two n cubed plus 2n cubed over 3 plus 2n squared. So which one is more costly? The first one is more costly, yeah? So you see, so the first one is more costly for large n, for large n. You see, because here you have an extra 2n cubed term, yeah? And here you have extra 2n square. I mean, for big n, then definitely 2n cubed definitely bigger than the 4n square. Okay. So that is question number 6. Okay, now we go to the next question. So the next question is number 7. So number 7, so essentially the whole problem is just saying that, you know, the matrix A has a special property that the condition number can grow to infinity for big N, yeah, for N go to infinity. But the determinant is always equal 1. Okay, so A is a very special matrix. So that, you know, when N grow to infinity, the size of this matrix grow to infinity, then the determinant is always 1. But the condition number can grow to infinity. Okay, so we can check that, you know, and A is defined like this and B is defined like this. So we can check that for N equal 5, then A and B multiply each other with equal identity. Okay, so let me do a quick check. So let me share the MATLAB and you can check that is the case. So now suppose I have A is, so let me get my matrix, yeah, so 1, minus 1, minus 1, minus 1, minus 1, and then 1, 0, 1, minus 1, minus 1, minus 1, yeah, then 0, 0, 1, minus 1, minus 1, and 0, 0, 0, 1, minus 1, and the last one is 0, 0, 0, 1. So this is a matrix A. You can see that lower triangle, lower below the diagonals are 0, diagonal equal 1, upper diagonal are minus 1. Okay. And what is the matrix B? So the matrix B look like this. So 1, then 1, 2, 4, 8. Yeah. And then 1, 0, 1, 1, 2, 4. Okay. And then 0, 0, 1, 1, 2. And then 0, 0, 0, 1, 1. Yeah. And the last one is 1, sorry, 0, 0, 0, 0, and 1. Okay, so this is your matrix B. Yeah. So you can see that the pattern here. So lower than diagonal are 0, the diagonal there are 1, and then on the above diagonal, then that's just a geometric sequence. Yeah, so 1, 2, 4, 8, 1, 2, 4. And now if I multiply A and B, I got identity matrix. Okay. So now we have to show that this one is correct for, you know, the general construction. So now this is a general construction. So suppose you have n by n matrix, yeah, then A is given by this definition. So if the row bigger than the column, then it's equal to 0. Diagonal, that's just 1. Then the row less than the columns minus 1. Okay, so you can construct the whole matrix. And similarly for B, diagonal equal 1, row bigger than the columns equal 0, and otherwise it of the form 2 to the j minus I minus 1. So we have to show that A times B is the diagonal, identity matrix. Okay, so we have to prove it. So now let me prove it on a piece of paper, because we cannot do this one by MATLAB. So how do we do it? Well, so we have to take the we have to take the definition of the matrix in the general form, right? So now if I consider the diagonal entries, okay, so remember now I have C equal A times B. C equal A times B, right? And now I consider the diagonal entries, so diagonal entries of the matrix C. Okay. So what is a diagonal entries? Well, so remember the general formula. So Cij is just the sum of Aik Bkj. Okay, so this is the general formula to get the entries Cij, k from 1 to n. Okay, so now I'm checking diagonal entries first. So diagonal entries is when I equal j, right? Yeah. So I just have Cii, right? And if Cii, then okay, so the sum above here just reduce to Aik Bki, right? K from 1 to n. Okay, yeah. And so now what is the trick? So the trick is now I split this one into two sums. So K run from 1 to I minus 1, Aik Bki. Okay, so far so good, yeah. And now the next sum will be K from I to I minus, sorry. The next one will be K equal I plus 1, yeah, because you stop at I already. So to n, right? And Aik Bki. Okay? And now you look at this Iik. So look at this one. So K here, okay, is between 1 to I minus 1. So you always have I bigger than K. Yeah. So in this term, yeah. Okay. So I bigger than K. Okay, because K stop at I minus 1. And now if you remember the definition of the matrix, okay, so if you go back to the definition of the matrix, so now the definition of the matrix, so now I write down maybe up here, yeah. So then we remember, yeah. The definition of the matrix is just, you can look it up in the question. So Aij is 0 if I bigger than j, equal 1 if I equal j, equal minus 1 if I less than j. Okay, so I bigger than k, so you can read as the row bigger than the columns. Okay, so you go back here, so the row bigger than the columns is only here, so the row I bigger than the column j, so therefore this one is just equal 0. Okay, so because of this I bigger than k, so therefore it equals 0. So similarly, now if I look at Bki, okay, so now again I have to write down what is the definition of Bij. So Bij will be, look at the question again, 0 if I bigger than j, okay, and 1 if I equal j, okay, otherwise it will be 2 to the j minus I minus 1 if I less than j. Okay. So now you look at this one. So you look at this one, yeah. So you see that k here is between I plus 1 and n. So k has to be bigger than I, right? So the row bigger than the columns. Row bigger than the column is this case equals 0. Okay, so therefore this guy equals 0 as well. Yeah. Okay. So you have 0 plus 0. So therefore just equals 0. No, sorry. I missed one term. I missed one term. You see, I missed one term, yeah. So you see this one k start from 1 to I minus 1, yeah. And this one k start from I plus 1 to n. So we missed the term in the middle. Okay, so what is the term in the middle? So k equal I, right? So the term in the middle is actually should be I, V, I, yeah. Okay. Remember, we start k from 1, we start at I minus 1, yeah? And here we start at k I plus 1 to n. So we missed the term here, I, B, I here, yeah? Okay. But you see now I is the diagonal terms, is 1. And BII is 1 as well. So this term is just equal 1. Okay. So now you have 0 plus 1 plus 0. So it's equal 1. Okay. So diagonal terms of the matrix C. So remember C is A times B, just equal 1. But it's a good news, yeah? Because, you know, I mean, we are checking that C has to be identity matrix. So now diagonal is equal 1. So it's good. Okay. So now the next step is what happens if off diagonal. So off diagonal, yeah. So now if j less than I, okay. So if j less than I, then what do I have? Well, I have Cij is sum of, again, k from 1 to n, Aik, Bkj. Okay, so now I split it into two sum. So k from 1 to j. Okay, then Aik, Bkj. And now the next term is k from j plus 1 to n of Aik, Bkj. Okay. And now you look at this term again. Okay. So this one is k is less than or equal j. Yeah. But remember j is less than I. J is less than I. Yeah? Okay. So what does it mean here? So it means that the row is bigger than the column. Right? So the row is bigger than the column. So therefore, remember, if the row is bigger than the column, it just equals 0. Yeah. So therefore, this one equals 0 as well. So 0. Okay. And now, similarly, you can look at this guy. Yeah. So you can see that this one k is bigger than j. Right? Because remember, k run from j plus 1 to n. So k bigger than j. And with k bigger than j, it means that the row bigger than the column. So the row bigger than the column, just equals 0. So just equals 0. So 0 plus 0 just equals 0. Okay, so this off diagonal Cij when j less than I, yeah. So when the row bigger than the columns, okay, it just equals 0. So row bigger than the column is mean that part that below the diagonal. Yeah, so the row bigger than the columns. Okay. So far so good, right? So now the next part is the remainder case, the remaining case. So remaining case is when you have j bigger than I. Yeah. So if j bigger than I, then again, so we have this Cij is the sum of Aik, Vkj, k from 1 to n. Okay. Now I split it again. So, but now I split it into five sums, 5 terms. Yeah. So first, I will let k run from 1 to I minus 1. Remember, I is the smallest number here, smaller than j. So I let it run to I minus 1. So I have Ik, Vkj. Yeah. And now when k equal I, then I put in Aii. Okay. Then Bij. Okay. And now I start again. But now k has to run from I plus 1. Remember, we stop at I plus 1, and here k equal I. So k has to run from I plus 1. But now I stop at j minus 1. Okay, so I have A, I, K, B, K, J. Okay. And now plus, I remember I stop at j minus 1, right? So now I have A, I, J. Then B, J, J. Right? Now I run again to the last term, so k equals j plus 1 to n. A, I, K, B, K, J. Okay. Okay, so now we look at term by terms. Yeah, we have 5 terms. Yeah. So we look at this one. Okay, so this one is I is bigger than K, right? This one I bigger than K, right? Because K stop at I minus 1. Yeah. So row bigger than the columns. Yeah. So therefore it equals 0. Okay. And now I look at the last term. Okay, so this one. Okay, so this one is K is from J plus 1. Yeah. So K bigger than J. Right. So the row bigger than the columns. So it equals 0 as well. Remember the matrix B, row bigger than the column just equals 0. Yeah. Okay, now what is AII? So AII is just equal 1. So this one is the diagonal entries. Yeah. And what is BJJ? So BJJ equal 1 as well. Okay. So this we can simplify a little bit. Yeah. And now, so I can write down, at least I can get rid of the first and the last term. Yeah. So now I have only Bij, okay, Bij plus the sum of Aik, Vkj, k from I plus 1 to j minus 1. Okay, the last term's gone. And this one is just plus Aij. Okay, so the first and the last terms are gone. Yeah. I is 1, Vj is 1, so that's why I have this. Okay, but now look at this one. Now look at the AIK. Look at this one, yeah. So what is going on here? So here, okay, so here you have K is bigger than I, yeah. K bigger than I. And if you remember, so what does it mean? So it means that the column bigger than the row, yeah. So column bigger than the row. So remember, this is the definition. Column bigger than the row. Column bigger than row, so it's -1, yeah. So then therefore this one gives you -1. Okay. And here AIJ as well. So AIJ, and now the J bigger than the I, because this is the condition here, J bigger than I. So equal -1 as well. Yeah. And now what you have left is just sum of, now you just have, okay, so what is Bij? So Bij, if you remember, now in this case, Bij, yeah, when J bigger than I, then it will be 2 to the J minus I minus 1. Okay. So then we put it in. So this one is 2 to the J minus I minus 1. Okay. And this one is, because the minus, I can take it out, so it become a minus, yeah. And you have the sum, and here 2 to the J minus K minus 1. K from I plus 1 to J minus 1. Okay. And the last one is -1. Okay, so far so good, right? And now let me expand the sum here. So let me expand the sum. So this one is 2 to the J minus I minus 1, yeah? And now I expand this sum, yeah? So I have a big bracket here. So if I put in K equal I plus 1, then I have 2 to the J minus I minus 2, right? Yeah. And then I put in K equal I plus 2. Then I have J to the, 2 to the J minus I minus 3. And so on. Yeah. So what is the last term? So the last term will be 2 to the J minus, so what is K here? So the last just is J minus 1. So J plus 1 minus 1. Okay, and then the whole thing is just -1. Okay. And now if you look into this, so this one, the last term is just 1. Right? So 2 to the 0. So 2 to the 0 is 1. So you have a -1 outside here, very far away here, but inside the bracket, yeah, you should just have 1 plus 2 plus 4 plus up to 2 to the J minus I minus 2. Okay, so you have outside just 2 to the J minus I minus 1. Okay, and this -1 just come down from here. Maybe erase this here, -1. Okay, and this one is just a geometric sequence. So 1 to the, 1 minus 2 to the J minus I minus 1 divided by 1 minus 2. Okay. And 2 to the J minus I minus 1 minus 1. So 1 minus 2 is -1. So -1 got cancelled with this minus, so become a plus. So then you have 2 to the j minus I minus 1 plus 1 minus 2 to the j minus I minus 1. And the last one is minus 1. You can see that this guy cancel this guy cancel this guy, so you have 0, eventually 0. So what did we do? We showed that the diagonal entries of C is 1. All diagonal entries are zeros. So therefore, the matrix C has to be identity. Okay. So what is the whole point here? So the whole point is now, so we go back to the definition, yeah? So what is the point? So the point is we want to show that, well, what is the determinant of A? So determinant of A is just equal 1, right? Because all the diagonal entries are 1, yeah? And you know, I mean, if you know that upper triangular matrix, if the diagonals are 1, you just take product of all the diagonal entries. And what is the condition number? So the condition number, so just take the norm of A in infinity norm, yeah? Then it will be n, right? Because remember the first row, all of them are ones. All of them are ones. You just sum it up, yeah? So then the maximal row has to be the first row, yeah? The max and absolute value. And the sum of n numbers 1 is just equal n. Okay? And what is A inverse infinity norm? Well, so this one is infinity norm of the matrix B. Okay, and if you remember the definition, so the matrix B, the very first row will give you the largest row sums in absolute value. So 1 plus 1 plus 2 plus 2 square plus up to 2 to the n minus 2, right? Yeah, because if you put in the definition, the last one will be n minus 2. Yeah. And what is this number? So this number will be 1 minus 2 to the n minus 1 over 1 minus 2. So 1 minus 2 is minus 1, so it will become 1 minus 1 plus 2 to the n minus 1. Right? So it's 2 to the n minus 1. So then the condition number, I mean, it's just the product of the two, right? Will be n multiplied by 2 to the n minus 1. And you see this one can go to infinity when n go to infinity. Okay, so what does it say here? So this say that the determinant, okay, determinant is 1. Determinant of the matrix is 1. But the condition number can go to infinity. So there's no relation between the determinant and the condition number. Okay, so we just show that there is a sequence of matrix AN, so that the condition number can grow to infinity, but the determinant is 1. Yeah. So now if we go back to the problems, so see, so we show that the condition number is n to the n minus 1, determinant is 1. But now the next question is, okay, so can you give example of a reverse situation? The condition number is, say, a fixed number, but the determinant can grow to infinity. So can you show that there is a matrix So that determinant can grow to infinity, but the condition number stay the same. So anyone, are you still there?
The double figure size is equal, yeah?
Huh?
The double large figure is looks like it's equal.
No, this one is very large, you know, so this one is been that very large. So essentially, it just say that, you know, condition number is say fixed and the determinant can grow to infinity.
Okay, so this one is mean the delta A is much larger.
Yes, much larger, yes.
Thank you.
Yeah, so that notation just means that much larger, yes. So now can you give example of a matrix that determinant can grow but condition number is fixed? Think of a simple matrix. Can you think of a simple matrix? Anyone? What is the simplest matrix you can think of? Well, should be a non-zero matrix, right? Because if it's zero, then determinant is zero, condition number is zero. Yeah. So what is a non-zero matrix? And very simple. So which one? Anyone? Take a very simple matrix. What is the simplest matrix you can think of? It's a random guess. Good point. Yes, identity. Yeah. But if you take identity matrix, determinant is 1. Yeah. So it's fixed. Yeah. And the condition number is 1 as well. Okay. But what happens if you multiply identity with a number? Okay, so now we expanded more, yeah. So now let me share the piece of paper. So now if you take a determinant, sorry, if you multiply the identity with say with a number say 2, right? Simple, right? So this one is 2i, right? Then determinant is what? So what is a determinant here? Somebody just say something. Yeah, so the determinant will grow. Yeah, why is that? Because in this case, determinant is just 2 to the n, right? Yeah. Okay, but what happened to the condition number? So this determinant definitely grow to infinity. Yeah. What happened to condition number? So what is A inverse? So what is A inverse of this matrix? What is, suppose I have two identity, yeah. So what is A inverse here? No. The inverse of this one is just, remember, if you have a diagonal matrix, the inverse, you just take 1 over the diagonal entries. That's 1/2, right? So everything is 1/2, yeah. Then when you multiply, then it's become identity, yeah. So A inverse, it's just you take everything here, you take 1 over that, yeah. So then what is the condition number? Say infinity norm, yeah. What is the condition number? So what is the condition number here? So what is the norm of A? What is the maximum row sum of A? Are you still there, anyone? So what is the maximum row sum of A? And what is the maximum row sum of A inverse? Yeah, 2 and 1/2, right? So what is just 1, right? So you see that in this case, then the condition number is fixed, is always 1. But the determinant can close to infinity, right? So in the previous problem, the determinant is 1, condition number grows to infinity. But in this case, completely opposite. Determinant is grown to infinity and the condition number is 1. Okay, so show you that the condition number and the determinant have no control on each other. Okay, so that is the whole point of the problem. And now we go to the next question. So the next question, this one is the same as the one in the practice. So now let me go to the practice. Yeah. So if I go to the practice, so part 1, we can show A equal LD L transpose by direct calculation. So I'm not going to do it. Okay. And part 2, you define the square root of the matrix D. Okay. What is, in this case, is the diagonal entries, everything take the square root. Then when you put it the same R transpose R, right? You can define the matrix R to be the LD square root transpose. Okay, then you get the matrix R. Yeah, and you can multiply out to get the value of the matrix R. So this one, suppose I multiply it out. Okay, suppose I put in MATLAB, I multiply it out, then you can see that it will be, so suppose I put in L is 100 minus a half 10101, and then the square root D is square root 200 and 1 over root 2 0.
Cannot see your screen.
Well, I just put in MATLAB, so maybe I can share the screen. Yeah, but you can put it in MATLAB as well. Yeah, so this one is my MATLAB. Yeah, so then I put in 0 1 over root 2 0, and then 0 0 1. Yeah, And then I multiply L times square root D. Okay, and do not forget the transpose. So we have to take the transpose of the whole thing. Okay, so if you put in the in that, then you get the matrix. Yeah. So now I put in my Google documents or Google Docs. Yeah. So this one should be transpose of the whole thing. The whole thing here. So we have to put the big transpose over the product of the two matrices. And you see, I mean, you can put into MATLAB and you get out the matrix. Yeah. So in this case, then I got root 2. I got square root 2 1 over square root 2 and root 2. Yeah. And you see, this one is a special case when you can find the Cholesky factorization. So then you have 0, 0 here. Actually, this one should be a minus, yeah. And then 1 over square root 2 and 0, yeah. So this one I just cut and paste from MATLAB output. And the last one is just 0, 0, 1. So you see the matrix R is upper triangular and all the diagonal entries are non-zero and positive, actually, and positive. And the third part, how do you show that the matrix positively definite? Well, first you compute the X transpose AX. Okay, and so you combine X transpose and R transpose into RX transpose. Yeah, because of this identity. And now this RX transpose RX become the norm, the two norms, yeah, of RX square. So it has to be greater or equal 0. And when Rx is equal 0, then because the matrix R look like this, so non-singular, you can substitute it in. So X has to be equal 0. So therefore the matrix R is positively definite. Okay. And so what is the next question? So the next question is how you use the Cholesky factorization to find A inverse. Well, you have to do two steps, right? So AX is identity. Then step 1, you have to solve. Well, so this one is equivalent to R transpose R. X is identity. So step 1, you have to solve R transpose Y equal identity, right? And step 2, you have to solve Rx equal Y. Okay. So this one is I mean, you can expand it out and maybe I just leave it to you to work out the details. Yeah. So if you look at the practice question, you see number 15 is repeated. So number 15 is repeated from a previous question. So if you look at 15, then it will be similar to I think it's similar to question 12, the last part. Okay. So you have so you can look it up and well, actually similar to this part. Yeah. Part 4. Yeah. So look for part 4 of, so look for part 4 of question 13. Okay, so just the same. Okay, so you have lambda max, lambda mean, and relative errors. So just look for that. And question 16. So 16 is exactly the tutorial problem. So tutorial problem. So tutorial week 4. We just did it, number 6. Okay. And then the last question, last question, look for part 4 in question 13 as well. Okay, otherwise I can post the solution during the weekend. Okay. So any other question?
No, just make sure you enroll us to the practical season with the MATLAB.
Uh,
Using practical.